Continue. And I was like to, before I forget, there's going to be wine afterwards, so that's easy enough to remember. So there's light at the end of the tunnel. Again, let me remind you that I'm going to, starting tonight, I'll post these notes on the webpage. So if there's something you'd like to look over. Okay, and so we're going to continue with this black box. And we're going to an algebraic variety. We're going to assign this object, this derived category of coherent sheaves. And we're going to study some of these properties and think of this, again, as some analog of function spaces. So there are many motivations to why you would introduce this gadget. And maybe, I think maybe the most interesting motivation, one of the more interesting motivations is going to come on Friday, where we're going to think of this gadget. We're going to see how this gadget comes from topological field theory. So how physics, in some sense, comes up with this object. So that's going to be maybe one other motivation for why to come up with this black box. So there it doesn't really appear as a function space, but we'll see the analogy with all the things we talked about before then. So what I'd like to do now is to give an example of this, in fact, of this kind of function space analogy of a kind of a Fourier transform for these kind of function spaces. And this is the first example, I believe, historically, which is the Fourier-Mukai transform. So here we're in a very concrete setting. We're going to start with A is going to be an abelian variety. So this is, in other words, this is a complex torus. This is a complex torus, looks like C to the G mod some lattice of full rank, which has the property that which is also an algebraic variety, which is also a projective algebraic variety. So it sits as a complex manifold in some projective space. And one of the first things we notice about this is that it's an abelian group. It's a quotient of CG by some lattice. And in fact, this abelian variety is equivalent to saying that this is a connected projective variety with group structure. It's going to have an abelian group structure. So, okay, so these are the objects. And now we'd like to see what kind of Fourier theory can we do for these objects. And let me denote the multiplication map as mu as map from A cross A to A. I'm also going to denote it as just by addition. I'm thinking of as my group structure additively. So now, so what are we going to do? The first thing we did in the Fourier transform is look at characters. We looked at the group of real numbers, and we assigned to it characters. So we should do the same thing, except that now our functions are going to be functions in this funny sense. So, but let's give a definition. And I'm just going to call this a character. You can put its various adjectives in front of or behind this, like call it a geometric character or a character sheaf. I'll just call it a character. Of A I'm going to just take as a definition that it's a line bundle. A line bundle L on A. So first of all, what's going on? I'm thinking of this line bundle as I can think of it. So by the way, everything throughout this talk means the adjective holomorphic or algebraic should be stuck in front of every word I say. So it would be a holomorphic line bundle, so I can think of its holomorphic sections on various open subsets of A. That's going to be the corresponding sheaf. So it's a line bundle on A with the following structure, an isomorphism, and this is going to be the character law. If I give you isomorphism L, the fibers of L of x plus y, isomorphic to the fiber at x times the fiber at y. Isomorphisms varying holomorphically. So how do I want to think of this as a character? Usually in a character we think of a function. To each point we assign a non-zero complex number. Here instead of a non-zero complex number I'm assigning a line, a one-dimensional complex line. So that's what a line bundle is. A line bundle I can think of as an assignment from points to lines. So it's a line-valued function on the abelian variety. And this is the analog of the property that the character is character of x times character of y, which we had in the definition of the Fourier transform. So this is the analogous property for line bundles. So, this is what I'm going to think of as a character. In order to say this statement a little more precisely and a little more nicely, I'm going to say, well, let's look at, I'm going to look at A cross A. And there's a multiplication map from A cross A to A. And so what does this statement say? This statement is really saying we have an isomorphism of two different line bundles on A cross A. So we have an isomorphism of the line bundle. On the left-hand side, we have the line bundle, which is the pullback of L. We take L on A and pull it back. So to any pair of points x and y, we look at the fiber at their product, which is x plus y. And on the other side, we have another line bundle on x plus y, which is just do L on one factor and do L on the other factor. Or if you'd like, in other notations, this would be pull back L along one direction and pull back L along the other direction. So there's these two projections, the x and the y. And we have a line bundle which just treats the two separately, and a line bundle that is given by the product. So this is what a character means. It's a line bundle together with such an isomorphism. Okay. So I'm going to use this as
abundance?
Is this in abundance? That's right. So that's a great question. So what are these given by? So the answer is they exist in I guess some abundance. So let me write the proposition saying what these things are. And this is a relatively straightforward statement, is that the characters of A, first of all, well, first of all, you can multiply characters by pointwise tensor product, and you can also parameterize them nicely algebraically. So they form, in fact, an algebraic variety, which is a group, and in fact, they form an abelian variety. So not only do they form a nice set, they actually form the points of an abelian variety. And which abelian variety is? It's the dual abelian variety. So the dual abelian variety, this is the dual of A. So the dual abelian variety can be defined in various ways. One way is to just take the dual vector space modulo the dual lattice, if V is the vector space. I take my vector space V, if A is V mod lambda, this is the conjugate dual mod the dual lattice. Or maybe a more familiar way to define this is just to say it's line bundles of degree 0 on A. We look at all line bundles on A, and we just look at the ones of degree 0. And the claim is that a line bundle of degree 0 can be made given this character structure, essentially uniquely. So that tells you exactly how much abundance. It's a space of the same dimension. It's just the dual complex torus. Before I say more about this, I want to say I want to rephrase the character condition in a way that's going to appear it's going to be useful later. I want to say, suppose I fix a point x and a. I want to break the symmetry of that picture. Suppose I fix a point x and a, then I have the map, which is multiplication by x, or just translation by x, which is a map from a to a. So I can say in terms of this symmetry, what we're saying is that if you take the character property, says that if you pull back L under this multiplication by x, well, you have a line bundle, and you're pulling it back by translation, you'll get another line bundle. But which line bundle do you get? I want to get just my same line bundle times a vector space. Well, in fact, times a complex line. Okay? So that's the same property I have over there, written in a non-symmetric form. So it says that the operation of translation takes L and doesn't perturb it so much, it just multiplies it by a one-dimensional complex vector space. So of course, for any fixed x, this is a silly thing to say, because a one-dimensional complex vector space just looks like C. But as x varies, this becomes a non-trivial statement. And this is what I'd like to call an eigensheaf. It just says it's an eigensheaf for translation, so eigen line bundle. You take the translation operator, and apply to L, and all you get is L times an eigenvalue. So now instead of eigenvalues, instead of numbers, are now vector spaces. Okay. So this is exactly, so a character is the same thing as an eigensheaf for translation. Yes?
When you write that sort of in the language of sheaves, do you mean that the Lx is a constant sheaf?
I mean Lx is just a vector space. So I could just take the sheaf.
Well, so how do you tensor vector space with the sheaf?
It's just a sum of, it's just a bunch of copies of, if you take, for example, a basis for the vector space, then it's just a bunch of copies of L, except that my vector space is one-dimensional. So this is just L. This is a funny way of writing L, but not canonically. The whole point is that this structure, this is isomorphic to L, but I can't pick this isomorphism in a consistent way for all x's. So really, the honest thing to say is this. I just want to interpret it. This is an isomorphism of line bundles on X cross. This is isomorphism of two sheaves on two line bundles on A cross A. There are no stocks in here. It's just here it's fibers rather than stock. But, okay. All right. So this is going to be a useful point of view. We're going to think of. So this is our first example of a kind of a Fourier operator. We have an operator, which is translation, and we are looking for the eigen things for this operator, just like exponential functions we could think of as eigen functions for differentiation. And we notice that the collection of these eigen things are not just a set, they actually form an abelian variety. So this is my analog for the dual group. We have the group of characters. This is, again, I can think of this as the group of characters. Okay, so now once I have this, I can now do a Fourier transform, because now I can look at A cross A dual. And now on A cross A dual, and for me A dual will always be, I just think of A dual as the group of characters. So it's this dual torus, but I'm thinking of it as the group of characters. So on A cross A dual, we can write a line bundle. This is called the Poincaré line bundle, which is a tautological line bundle. It just says, if I want to figure out what's the fiber of this line bundle at a point X and L, so here X is an A, and L is a character on A, which I think of as a point as A dual, well, I just take the fiber of L at X. Okay? So this defines a line bundle on the product, or if you'd like, if I take the preimage of L, I have a copy of A, and I put that line bundle L on the copy. So there's a universal line bundle on this product. And I'm going to think of this as the analog of my e to the ixt, which is a function on R cross R dual. It's really the dual line, which is that for each particular value of t, you take the corresponding character as a function of x. So now I can do a Fourier transform with this. So now I have all this machinery set up, so I can do a Fourier transform, which is a functor from, I want to do it this way, just like I did in the, I'm going to go from right to left, just like I did with the usual Fourier transform. I get a functor from here to here, from functions on A dual to functions on A. And what is that given by? It's given by this general formula that we said for the way we describe all functors. They're given by integral kernels. You integrate along the first factor what you got by pulling up along the second factor times p. So this is the analog of integral along pi 1 of pull back of a function times e to the ixt. Okay? So this is the functor given by, so here again, these are pi 1. If I forget to write, pi 1 will always mean left. Pi 2 means right. So this is a functor, and it's now defined. It's a functor between these derived categories. And then we get this theorem to Mukai, which says that this is an equivalence. So it's an equivalence of these derived categories. And its inverse is given basically by the same formula up to some science. So this is the statement of the Fourier-Mukai transform. So what does this mean? Is that still visible up there? Okay. So what does this mean? This means, i.e., any sheaf on A can be written is an integral of characters. right? Because so this is the exact analog of the Fourier. The fact that the Fourier transform was isomorphism says that if you give me any function on R, you can write it as an integral of e to the ixt's, some continuous linear combination of the e to the ixt's. And now we're saying that this is again an equivalence. Any sheaf on A, you can get this way. In fact, you know what the coefficients are. They're given by the inverse Fourier transform. Any sheaf comes as an integral of this Poincare line bundle, which is just a collection of characters. So maybe to be a little more specific about it, so what can we apply this functor to? For example, let's take a skyscraper. So what a skyscraper means, I'm going to take, let's call it O sub L. So this is a particular kind of object in this derived category. That means you take the point L, is a point of A check, and you take the one-dimensional vector space sitting at that point, and 0 elsewhere. So it's a kind of the analog of the delta function. And we know that delta functions under Fourier transform go to the characters themselves. So the same thing, you take this skyscraper, you take this delta function here, you pull it back, you're going to get just a single fiber. You get something that's 0 on A cross A check, you get something that's 0 outside of that fiber. So when you project the other way, you're just going to get a line bundle, the line bundle on this fiber. In other words, Fourier takes O of L to the corresponding L itself, thought of as a line bundle on A. That's what Fourier transform is supposed to do. You take so in other words, points, so this is the same kind of picture. Points become characters. Points of a dual are exactly given by characters. And the transform is kind of determined by this. If you know the Fourier transform on delta functions, you kind of write any function as a linear combination of delta functions. And that tells you the transform. So this is an example of how this works. And what other properties did we want of the Fourier transform? So one property was it really is a kind of, it really parameterizes characters. It takes characters to points. The other property we wrote was the fact that it diagonalizes the action of the group. So one way to say that was that convolution got taken to multiplication. Convolution of functions on R gets taken to multiplication under Fourier transform. And the same thing is true here. If we take, let me define convolution. What is F convolution? If I give you F and G are sheaves, so in, say on A check, so I'm going to define the convolution to be just the integral of F. What's convolution? It's integral of F in one factor, G on the other factor. So I have this map. I guess I'm writing it for the dual now. I have this multiplication map. And the convolution just means put one on one factor, put the other on the other factor, and integrate together, get a single function. And so this is the definition of convolution. And the Fourier transform, again, takes convolution to tensor product. So here I'm just writing a check to mean, so here check equals F. Okay. So this is a key property. So maybe an example of this is if I take a skyscraper at a point L, and I convolve it with a skyscraper at a point M. So here L and M are both characters. Then what does it mean convolution? This just means you add this is just L tensor M, which is the group, just the groups. So convolution on skyscrapers is just the group law. It's just addition.
But when you say a sheaf,
Yes.
what you actually mean is a complex.
Absolutely. So that's part of the lie that's going to persist throughout this.
From now on, whenever you say sheaf,
Absolutely. I mean complex.
in fact, a complex.
Yeah, and maybe I should clarify when I actually do have sheaves. So in this case, these skyscrapers honestly do go to line bundles. So they're actually sheaves. But and in fact, and again, this is true here. These are the convolution of these two skyscrapers is again just a normal skyscraper, and it gets taken to a tensor product of line bundles.
But in the example, you apply the functor
Yeah.
and then just have tensor M.
Yeah, that's right. So here it's just, and then I apply Fourier to this. The Fourier of OL is L. So under Fourier, this becomes L, this becomes M, and this becomes L tensor M. So that's this, this formula here. Okay, so this is the statement, and again, another lie that's going to happen is when I say tensor, in general, it's going to mean a derived tensor. The word derived will be, and complex are going to be omitted consistently. So that's why we went through that in the first hour, so I don't have to say it ever again, unless asked. Okay, so this is an example of the Fourier transform in action. Now I'd like to. Well, we have this already. We had this original Fourier transform on the real line, and there's a version of the Fourier transform in this crazy world that looks a lot like that. And what I want to do is I'm going to now introduce a new class of functions. So after now we've spent some time getting to know these O modules, I want to introduce a class of functions, and I was asked to apologize before I say these words. So now I'm going to talk about D modules. Yes. Right, so eigensheaf becomes, multiplication. The action of multiplication becomes just tensor product, right? So eigensheaf was saying that you're invariant under translation up to some number, up to some coefficient. When you Fourier transform that, translation becomes multiplication. So you want, yeah, that's a good thing. It's a good question. So what does it mean to have an eigensheaf? What happens to eigensheaves under Fourier transform? Well, you already know the answer because I told you eigensheaves are the same as characters. But let's see it in a different way. If I know that I have a sheaf f, and I know that when I translate it, it gets taken to itself up to some coefficient, up to some line. Under Fourier transform, this means I get a sheaf which when I tensor with a line bundle, it becomes, it's isomorphic to the sheaf again up to some coefficient. So you want a sheaf that doesn't matter what line bundle I tensor it with, I basically get the same thing. I get a one-dimensional complex vector space times my thing. So how can that be? How are you going to get a sheaf that doesn't feel tensoring with line bundles? Well, if it's a skyscraper, if it's located at a single point, then when you tensor it, all you're going to feel is the fiber of that line bundle at that point. Nothing's going to happen under tensor product. So under skyscrapers, this is exactly what happens to skyscrapers. They just get multiplied by a one-dimensional complex vector space. So here I want to write. I mean, this is a silly thing. It's multiplying by one-dimensional complex vector space. But that's why these characters become skyscrapers.
Would it be O of L?
Yeah. So. It's L at L sub. I mean, it's a fiber of a line bundle, but it's isomorphic to C. It's some one-dimensional complex vector space. So this is going to be useful later. It's the fact that this complicated, well, maybe it doesn't look so complicated, but the idea of being invariant under translation up to line, on the other side becomes an eigenfunction for multiplication, and eigenfunctions for multiplication are just delta functions. That's what diagonalization. That's why we're doing all of this. It's to diagonalize these translation operators. So all this is going to get much more complicated when we start doing these in a non-abelian context. And that's what we're going to start tomorrow. But before that, I want to introduce other questions about this? Okay, I'd like to introduce the language of D modules. So what are D modules? This is an important variant of O modules. And what it's going to be is instead of looking at functions, we're going to look not just at functions, but we're going to look at functions together with their derivatives. So now I want to spend the rest of today explaining what this means and what D modules are. So first of all, what is D? So if I have X as an algebraic variety, so everything is, let's say, of a smooth variety. What do I mean? For example, just take an elliptic curve, or e.g. A as an abelian is a torus, an abelian variety. So this is the kind of spaces I'm going to be looking at. What is D? Dx means the associative algebra. This is associative algebra. This is the algebra of differential operators on X, but algebraic differential operators. So it's generated by functions and by vector fields. So what is a differential operator? Something that involves multiplication and differentiation, possibly many times. So I'm going to look at associative algebra generated by multiplication by functions and by differentiation with the relations with the Leibniz and product rules imposed. So in other words, if I have a vector field and I have an operation given by a function, so here del is a vector field, f is a function, I want to say that del f minus f del, the operators don't quite commute, the difference is the derivative of f. Okay? This means any function and any vector fields are exactly things that differentiate functions. And if I have two vector fields and I apply them in different orders, well, I already know vector fields already have an operation on them, which is the commutator. And I want the commutator of vector fields to be given by the commutator in this algebra. So maybe the first thing you'll complain, possibly, is that I said there aren't very many functions. So when I say this, I mean on a level of sheaves. What does this mean? And this means that, like everything else in these lectures, I'm going to be working on each open set. So on each affine open, you do this. You look at polynomial functions and polynomial vector fields, and you look at the algebra they generate, and that gives me a sheaf. So I'm going to think of this as just an associative algebra, but what it really means is that on each open set I have an associative algebra. Okay. So there, for example, one place where I don't need to look sheaf-wise, for example, take the affine line. Differential operators on the affine line is just the Weil algebra. It's generated by, well, functions is generated by multiplication by x. Vector field is generated by ddx. And you just have the Heisenberg commutation relation between them. So that's the algebra of differential operators on the affine line. So this is the Weil algebra, or I guess Heisenberg, I don't know. OK, so this is the algebra of differential operators on A1. So what are D modules?
Wait, are we looking at the algebraic vector field?
Yeah, algebraic
There's
vector.
no D bar here.
No D bar. Everything is polynomial. Right.
Just D. Okay.
Right. Everything is polynomial vector fields, polynomial functions on each open set if needed. And I look at the algebra. So these are algebraic differential operators. So now I want to look at how to think of D modules. And I want to give 4 different pictures for how to think of a D module. So I mean, a D module is going to be a module over D. That's what it is. D module is D module. OK. So great. So we know what a D module is, but how do you think about them? And so there are many different ways in which D modules come up and where they are going to come up in this week. So let me start with the first one, which is I want to motivate D modules the same way I try to motivate O modules. So how did I try to motivate O modules? So I want to think of these as some kind of generalized functions. And the idea is that I thought I tried to motivate O modules as generalized functions. I'm going to try to motivate D modules the same way, but they're going to have more information. So what do I mean by this? Suppose you're studying, you're trying to do Fourier theory. You have this e to the ixt. And you think, well, e to the ixt lives inside of some functions, some kind of functions. Well, it lives in lots of, say, smooth functions on the real line. And you say, well, e to the ixt is not an algebraic function. So how am I going to possibly see e to the ixt in algebraic geometry? And I say, well, OK, it itself is not, but I'm allowed to multiply it by polynomial functions or polynomial vector fields. So what I'm going to say is I'm going to take e to the ixt, and I'm going to multiply it by differential operators. So these D, for me, always means algebraic differential operators. So if you look at e to the ixt, you look at them, all algebraic differential operators applied to it. Well, this doesn't give you so many different things, right? But so what I want to look at all functions I get by multiplying by algebraic differential operators. And this is an example of a D module, because I can now multiply again on the left. So to the function e to the ixt, I've assigned a module over algebraic differential operators. And the point is that this module, let me get rid of the I for simplicity. So what does this module look like? It's not such a crazy module. This module basically knows everything about the exponential function. So this module, well, it's generated by a single thing. And so it's generated by, it's a quotient of D by some relation, by some ideal. And what's ideal do you get? Well, this is annihilated by, if you differentiate and you multiply by lambda, this is an algebraic differential equation satisfied by e to the lambda x. So you get this module. It's differential operators modulo this ideal. So it ends up looking like, so this looks like polynomials in x times e to the lambda x. Because you have this relation, all the differentiations become multiplications. So as a module, it's not very large, but it remembers about the exponential function. This is so because exponential functions satisfy an algebraic differential equation, so this, this remembers, I can recover the exponential function e to the lambda x up to some scalar multiple. These are the only functions that satisfy this equation. So I'm basically recovered not e to the lambda x, but this one-dimensional vector space, if you'd like. So these are what happens if I look at solutions to these differential equations. I get just e to the lambda x up to scalar. So this is a really good algebraic substitute for the this function. It remembers it up to a scalar. So this is an example of what's going to be called a holonomic D module. Holonomic D module. So a holonomic function is something that satisfies nice algebraic equations, which means that when you look at this module, you get something small. It satisfies a lot of relations. So I don't want to be too precise yet about holonomic, but this is sort of one thing, one example. So what's another example of a D module? Another example of a D module, and I'm going to think of this living on the affine line. These, as D modules have affine lines, so I'm kind of switching from R to C. I'm looking at the affine line over C. But what's another example? Let's look at delta function at a point lambda. So again, this is not an algebraic function. It's not even a function. But we know that you can take the delta function and differentiate. You can multiply it by an algebraic function, by a polynomial, or you can differentiate it by a polynomial differential operator. So this lives in some kind of space of distributions. But I don't really care exactly where it lives. All I care about that this is, again, an example of a D module. Look at the delta function, all of its derivatives, and all of their products with functions. So what does this look like? Well, this looks like differential operators. And there's, again, an equation that's satisfied, which is that if you multiply the delta function by x, you get lambda. So x minus lambda annihilates the delta function. So, or if you'd like, this is isomorphic. As a module, it looks like polynomials in del times the delta function. So it's a very small module. This is an example of a holonomic module. It looks much smaller than D, right? D looks like polynomials in x and d dx. These look like polynomials in only one of the two variables. They're kind of half the size of D. So this is kind of half the size, and I'll say this a little more precisely later. This is half the size of D, which is what is called holonomic. So these are small modules. So what can you do with it? So the point is we can now try to actually do a Fourier transform in algebraic geometry. We have we have exponentials and we have delta functions. So in this world of D modules, you have great substitutes, both for, again, from that module, you can recover the delta function up to a scalar. So we have things that really know about exponentials and about delta functions. And so now what we can do a Fourier transform. So how do we do the Fourier transform? The usual Fourier transform, but in this module language. So what's the usual Fourier transform? So D, I'm going to look at the affine line, this Weyl algebra that appears right here. And you notice that this Weyl algebra has a symmetry. You can exchange x and d dx up to a sign. So we can, there's an involution on this. There's an automorphism of this algebra, since x to d dx and d dx goes to x with some sign. So this is a symmetry, and this is what happens under Fourier transform, right? That multiplication becomes differentiation. So we notice that this is a symmetry of the algebra D. And so this gives me a symmetry of the category of D modules. There's a functor, and there's even nothing derived. This is one of those very rare occurrences in this week where there's nothing derived. You just take modules over this algebra, and modules of this algebra, and there's an equivalence. Given a module, you just change the role of x and d dx, and you get a new module. And this is an equivalence of categories. And indeed, if you look at the definitions of the modules of the delta function exponentials, they get exchanged. So this is the Fourier transform. It takes delta functions to exponentials. So if you'd like, the D module e to the lambda x gets taken to the D module delta of lambda of t, whereby the quotations, I mean that we're thinking of these as D modules. So in other words, that says that any D module on A1 can be written in the basis of exponent. This is, I want to say that any DA1 module is an integral or linear combination of delta functions, of exponentials. If you like, but the statement that this is an equivalence of categories. And in fact, if you like this Fourier transform point of view, you can write that Fourier transform in exactly the same way. You look at A1 cross A1, and we have these two projections. So maybe I think of one of them as being x, and one of them as being t, the t variable. And on here, I write a D module on A1 cross A1, which is spanned by e to the ixt. It's a D module in two variables. All the differential equations satisfied by e to the ixt. And so now, if we have a formalism, which I haven't explained, of pull back, tensor, and push forward for D modules, you can get the exact, so the same Fourier transform is given exactly by the same formula. It's pi 2 push forward of pi 1 pull back of f tensor this e to the ixt, where these are appropriately defined operations on D modules. The pullback you can guess, it's just pullback. Well, OK. Yeah. So pullback just means, well, OK, I'll explain in a second in a different point of view. And in the push forward means you solve the differential equations along the fibers. So when you integrate, you just think of what are the differential equations satisfied with the integration of a function. OK, so this is one point of view. This is one thing that's nice about D modules is that you can really mimic things that you have. You can now think of all your favorite functions from harmonic analysis. A lot of them satisfy algebraic differential equations. And you can now have a world inside of algebraic geometry in which to capture them. So that's one main motivation for studying D modules. OK, so now, OK, so what's another motivation? So so now the second picture I want to give is I want to say that D modules are something like O modules on a non-commutative space on the quantized cotangent bundle of X. So this is the second picture I want. So it's a kind of a non-commutative picture of this. So what does this mean? So let's look at this algebra of differential operators. It was generated by functions and vector fields. Did I? No, I erased that. With these two relations, del f minus f del is f prime, and commutators are commutators. So now del 1 L2 minus del 2 del 1 is the commutator. Now, let me throw in an h bar into the picture. And where does the h bar go? It goes here. So I'm going to think of this as an algebra with a parameter. I've now defined an algebra with this parameter h bar. And what happens when h bar is 1, or in fact, if h bar is non-equal to 0, you can rescale it away. You can just change your basis. And you get just the algebra D. As long as h bar is not equal to 0, your algebra is going to be just D itself. You haven't done anything. But what happens when h bar equals 0? These relations have gone away. They've become del and f commute, del 1 and del 2 commute. So you get this differential operators with h bar equals 0 is just the commutative algebra generated by these two, by functions and vector fields. So it's what you would call the symmetric algebra of vector fields over functions. This means a commutative algebra generated by vector fields and as a module over functions. So this just means you're allowed to have functions and you're allowed to have a bunch of vector fields and multiply them in any order you want. And commutative algebra. So what does this mean? What is symmetric algebra of vector fields? Well, vector fields are linear functions on the cotangent bundle. So polynomials in vector fields just means polynomial functions on the cotangent bundle. So you see that this algebra of differential operators degenerates when you put in this parameter, nothing happens away from the parameter equals 0, but at the parameter equals 0, you just get functions on the cotangent bundle. So this is what's usually known as the symbol map. These are symbols of differential operators. But the way I want to think about the symbol map is that this is a nice degeneration. So this is a nice, where nice means technically is the word flat. It's a flight degeneration. Or I get, maybe I'll turn things around. I think that of a nice deformation, so that the algebra D is a nice deformation of functions on the cotangent bundle, where all of a sudden things have become non-commutative. And if you think of the cotangent bundle as a symplectic manifold and you like quantization, star quantization, this is a quantization of functions on the cotangent bundle. So how do I want to think of D modules? I want to think that D modules are, well, we know how to think of functions on the cotangent bundle. Modules over O of T star x, these are things like vector bundles on T star x. So this just means, let's assume we understand what O of T star x modules are. So D modules, so in other words, so D modules are O of, so this is a kind of a meaningless statement. But I want to say that their modular, the differential operators are functions on a non-commutative cotangent bundle. I can't really take spectrum of this non-commutative algebra, but I kind of want to think that its spectrum would be this quantized version of the cotangent bundle. So, so this is one picture. So in this picture, you can try to ask if I give you a D module, then I want to think of D module as something like a vector bundle or some kind of sheaf on the cotangent bundle, but everything has kind of gotten a bit fuzzy. And how does things become fuzzy? Is there's one point is the Heisenberg uncertainty principle, and what Heisenberg uncertainty says in this kind of context is that D modules look like sheaves on T star x with big support. So what does this mean? If I take a D module, I want to think of some kind of a classical approximation, or some kind of shadow of it is some kind of sheaf on the cotangent bundle. But the point is I can't get anything on the cotangent bundle this way. So what are the smallest things you could do? Look even in this one variable case. We could get something that looked like polynomials in x, and we can get something that looks like polynomial in del. But we didn't write an example of a module that's a one-dimensional vector space. You can't write a one-dimensional vector space as a module for this D because you need this commutation relation x and del equals 1. On a one-dimensional vector space, they would automatically have to commute. More generally, what you find is that the D modules correspond to, so they have these kind of, they look like polynomial. The smallest you can get is polynomials in half of the variables, either all the functions or all the derivatives. So you can, so let me, right, so maybe let's say that the smallest D modules correspond to half the, geometrically can only be supported on half the variables. They correspond to Lagrangians in T star of x. Okay. So the smallest kind of support you can get is a Lagrangian, which means half the dimensions. So you can either tell all of the positions exactly, or you can tell all of the momenta exactly, but you can't tell both. Okay. So these ones are called, these smallest D modules, these are again the ones that are called holonomic. Okay. So this is kind of, again, maybe a caricature of D modules, but it's a very useful one. That D modules are the same kind of universe as O modules, they're just in double the number of variables. Okay. Questions about this? Right, so what do I mean by support? I mean a kind of shadow, a kind of symbol. So one way to define that is if I give you a, so I mean this is of course not a precise statement because the support of a D module is not really a sheaf on the cotangent bundle. But if M is a D module, I can, right, so I get it gets a shadow, which is some kind of sheaf on the cotangent bundle, which is not completely canonically defined, which is some kind of a shadow. So how do I do this? One way to think about this is that D is itself filtered. It's union of differential operators of order less than equal to I for every I. So D is a union of differential operators, so it's filtered by order of differential operators. And one way to think of passing from D to functions on the cotangent bundle, that functions on the cotangent bundle are the associated graded of D. That's instead of doing this H bar business, I can say that what I'm really getting rid of is the non-homogeneous terms. So I'm just going to the associated graded. So given a module over differential operators, I equip it with the appropriate filtration and take the associated graded, and I get an honest sheaf on the cotangent. Yeah, and then I take the support of that. So that's technically what I mean. That's called the characteristic variety, or singular support. But maybe I'll just leave it as a caricature for now.
Suppose we start, you do it the other way. Suppose we start with a sheaf on T star X.
Right, and you can.
Does the deformation then determine a D module?
Maybe. I mean, you could try. So if I give you a sheaf.
Sort of a symbol calculus. Is there a
Yeah, I mean, but it's obstructed. In other words, if I give you a point on the cotangent bundle, it won't deform. There's no way to take a point and deform it to a cotangent bundle. If you take something that's Lagrangian, or more generally coisotropic, then you have a hope. And there is a kind of way to say what the deformations are, how to lift, what happens on the category of O modules as you deform. So there is a kind of a strong relation between D modules and sheaves on the cotangent bundle. But for me, I just really want to think of this as a kind of a picture. So in any case, the category of D modules is a deformation of the category of sheaves on the cotangent bundle. But not everything survives. Some things vanish. OK. So that's another caricature of D modules. Now, let me do maybe the most important one. So I want to give another picture. What is a D module? So this picture is D modules are sheaves with flat connection. So what does this mean? So if I take E is a vector bundle, say. So suppose I have a vector bundle. What does it mean to, how do I give a vector bundle flat connection? With a flat connection, if I give you a vector bundle with flat connection, this is the same as giving an action of differential operators on E. So why is this? Well, we already know how to act by functions. We already know how to multiply E by functions. We know how to multiply sections of E by functions. But what does the connection give me? Connection tells me how to act by vector fields. A connection tells me that if I have a vector field and I have a section, I can differentiate. And what does the flatness mean? Flatness means exactly, so the curvature is the lack of saying these relations are not satisfied. Curvature equals 0 means del 1, del 2 minus del 2, del 1 acts as the commutator. In other words, the relations of this algebra are satisfied. And so you get a well-defined module over this associative ring. This associative ring is generated by functions and vector fields, and you have imposed this relation by saying the curvature vanishes. So giving an action of D on a vector bundle is just saying all it's saying is giving an action of vector fields and asking for it to be flat, asking for it to be compatible with commutators. So in general, you can say the same words, replace a vector bundle with your favorite sheaf. And you can define what does a sheaf with a flat connection. It again means the same thing. You have an action of vector fields, and commutators act by commutators. So we don't usually think so often about flat connections on things that are not vector bundles. But we're going to, but that's exactly what a D module is. It's just a flat connection, but now on a sheaf. So maybe one way to paraphrase this is so I can say as a kind of analogy that O modules are to vector bundles as D modules are to flat vector bundles, vector bundles with flat connection. So that's kind of a powerful analogy to how to think of this. So we know that not all O modules are given by vector bundles. Similarly, not all D modules are given by flat vector bundles. What does a typical D module look like? So typical D module, well, it's going to look like it's going to be built out of flat vector bundles, but not on the whole space, on subvarieties. So there's a similar picture for O modules. An O module can be thought of as something that's a flat vector bundle, not on the whole space, but there's some stratification. On each piece, you have a vector bundle. So nice D modules are going to be, these are exactly the holonomic ones that I've been talking about. They can be thought of, you look at your space and you write it as a union of subvarieties. On each one of them, you put a flat vector bundle, but then you're not quite there yet. Because if I give you a flat vector bundle on a subvariety, I know how to differentiate it along the subvariety, but I need to be able to also differentiate normally, in normal directions. So I have to throw in the normal derivatives kind of for free. So what's the example we saw is delta functions. I have the affine line. I take the point here, and I take the flat vector bundle on a point. In other words, just a vector space. But if I want to make that into a D module, I need to be able to tell you how to differentiate transversally. So I just add that for free. I just do polynomials and derivative times this delta function. And that was the D module we wrote. Okay. So this is an example of a D module. It's sort of supported at this point. It has this one-dimensional vector space plus all you threw in all these extra derivatives. So that's, yeah.
When you say build out, you mean in the derived integral?
Yeah, so, well, I guess there's several ways to make this statement precise. One way to say it is if I give you a holonomic D module, then there's a stratification, such that if I restrict to each of the strata, I get just a flat vector bundle. In the derived category, you can say that you can make it out of triangles, out of vector bundles on subvarieties extended. But you can just say it's restriction. There's a stratification on each strata. It's just a flat vector bundle.
It no longer lives on the point. So
Sorry?
after you throw
Right. It almost lives on the point because if I take the second derivative of delta, it's no longer killed by multiplication by x. It's killed by multiplication by x cubed times the delta. If I look at the delta function on 0, so it almost lives on the point. Every thing in here is killed by high enough power of multiplication of the coordinate. So it lives right near the point.
What about, for instance, the idea of the points?
Right. So then another claim is that if F is a coherent sheaf, so if it's so it's really some finite dimensionality, and it's a D module, then it's actually just a vector bundle. So there are no interesting coherent sheaves up here. Like, for example, the skyscraper at a point, I wanted to make it into a D module, but I needed to throw in this infinitely many. This is not a finite dimensional vector space anymore. So I don't get coherent things because I always have to throw in these normal derivatives. So the ideal sheaf of a point won't be a D module unless you're in one dimension. So, OK, so there's, OK. Now, and maybe I'll just mention a fourth motivation for D module, a fourth picture of D modules. And this one won't really appear so much until Saturday. But this is, in some sense, the most important one for both in terms of in the geometric Langlands program, both in terms of some of its original motivations and in terms of the tools that are actually used. The D modules, so I'll just mention it briefly and discuss this in detail on Saturday. The D modules are very closely related to representations of Lie algebras. And let me just say what I mean by that. Suppose I have a space X and a group, I know what it means for a group to act on a space. So if a group acts on a space by holomorphic maps, the Lie algebra of that group acts by vector fields. If I differentiate the action of a group, every element of the Lie algebra gives me a vector field on the space. So this tells me that what is the universal enveloping algebra of the Lie algebra? This is the things that are generated by by the Lie algebra, freely generated by Lie algebra, with the one relation is the commutators. So UG will act on X by differential operators. So if I have a group acting on a space, then its enveloping algebra gives you differential operators on that space. And so, for example, functions on X will be a representation of UG, representations of the enveloping algebra. And in nice cases, and this is maybe the main point, is that nice spaces X, then D modules, that the relation between D modules and UG modules is essentially an equivalence. Maybe to say that, maybe one more sentence to add to that. If UG acts by differential operators, what is that good for? Well, if I give you a D module, if M is a D module, that means that I already know how to act on M by differential operators, by all differential operators. So in particular, I know how to act on it by these particular ones. So if I take its global sections of M is a UG module, or if you'd like, this is the same thing as just as a G module. So you can think of D modules as a way of producing examples of representations of Lie algebras. If I give you a space on which a group acts, then any D module on that space gives me immediately a representation of that Lie algebra. So this is sort of the main motivation from representation theory, to study D modules. Okay. Okay. So yeah, I guess it's in bad form to go over on the first day, so I think I'll stop there and remind you that there's wine upstairs.